want to distinguish in there, but in the way we really put that together, that's how it looks. So the N may have a high degree. Anything else, any other nodes should not. Okay, so this is one. So that's what happened. And of course we had to make some other changes. I'm not going to go too much into details, so I see you're already reading. But we're going to... No, I know.
No, they have a class, that's why.
Yes, I know. So let's see what other examples can we give. We have sometimes questions that are very similar. I mean, that was written there also. So we are able to put two questions that are very similar. For instance, you see here, there is a question 2.9, and if you are going to look at the main, PowerPoint presentation, you see that these two questions are very similar. So those who are close to this have an advantage. And we're able to put them together into one question and put this question high up. Okay? It is very, hard work. Okay. Then there are some questions that are necessary because of where they are placed. So that does with a different example. And there are also filter questions that go direct to the end. I mean, separate some population that's not going to be asking other questions. Like, for instance, I said there was someone who was going to be asked, who did not finish an education program that was ending in a certificate. Okay, well, I don't think I'm going to go much more into this detail. Some examples, and these are some of the work where we're trying to apply, I have done some work in the chemical molecular structures, where we're applying also GRAPHS theoretical tools to the structure of molecules, and we're trying to also apply this to questionnaires. All right, so let's go to, so this is basically the long-term objective. Figuring out with the data we have, what would be an ideal questionnaire. And having one questionnaire that is given to us to create something, we find some kind of distance between that questionnaire and the optimal one. Okay? And of course we want to use all these maximum information principles that discovered by Picard and to use this distance at that point. That's it with the first part. With the applied part, which is the newest thing I started. And this is a more pure part. That deals with transformations on diagrams. Well, let me explain to you what do I mean by this. Why did people come up with this? Well, this is one reason. There are many reasons. There's, for instance, one of the first transformations defined was the transformation for a line graph. Okay, and one of the reasons was, which in the end proved to be helpful, but it doesn't matter. Sometimes we do things for one reason and then after they are good for other reasons. So let's look at this graph. It's a famous graph. It's called Peterson graph. And books have been written about it. It has a very interesting problem. And one of the properties I'm trying to actually, so it has a pentagon on the outside, and then has another 5 vertices on the inside, each is connected to one of those outside. Inside it has another pentagon, but it appears to us more like, so it's another cycle, it appears like a star. Okay, so this is Peterson. Very well famous, all kinds of properties. But one of the questions that also sounds, it is applied, but it has been studied tremendously. And still we know almost nothing about it, is being Hamiltonian. When is the graph Hamiltonian? characterizations for various classes of graphs, but we don't have any single chapter. What does it mean to be Hamiltonian? Very simple to explain. In a graph like this, is there a cycle? This means you can start anywhere, basically. That goes exactly once to each vertex. Okay, so this is one of the vertices. And goes back. Well, this graph is not like that. It can be proven, you see, it's a lot of symmetry in this graph. It can be proven that it's not Hamiltonian. However, it has many other interesting properties. For instance, if you take any of the vertices out, and the arc, and the edges that are connected to it, it becomes Hamiltonian. The rest is Hamiltonian. Okay, which is, can be easy to see. You know, you just go like this, and that. Okay? Any of them, inside, outside, and so on. So this is one problem. However, it's very difficult to prove that the graph is not, and it's from a computation point of view, it's hard. It's one of the hard problems. Now there is something that sounds very similar. Another definition, Eulerian. You heard of Swiss mathematician Euler. So he's basically, the name graph theory and so on, so he uses a lot of stuff. Eulerian. What do we say that the graph is Eulerian? Sounds pretty simple, and there are, Königsberg bridges and so on, a lot of problems linked to that. It's the same thing, you start in a point, but you have to go on the edges. Exactly one through each edge and come back. Now this problem of being Eulerian is solved. It's completely solved, basically, whether it's theoretic or not theoretic. Basically, all you need to do, it's even local. So basically you can just look locally at each vertex, know if the graph is Eulerian or not. And how you reach if the degree is. That's all you need. For instance, here it's 3 to know already, it's not very Eulerian. And if you want to make this Eulerian, you'd have to do what you see, you have to add. You want to just by adding edges to make this Eulerian, I don't know, you have to add in such a way that each of these, since you cannot delete anything, suppose that's a problem, you have to add edges so that each degree is even. So basically you are going to add, so here it's 5 from the outside, 5 from the inside, 10 points. Okay? Now this means that you have to add 5, exactly, thank you, edges, right, to make this Eulerian. And if you want to do it, since this is so symmetric, you could try something like this, right? I don't know if that's how it works. Alright, so something like that. I'm going very symmetric here. No, okay, and notice that these are the points, right? The points are the ones. Okay. Where should I go with this? Here, right? Okay, and here, something like that. Alright, so now, this is not the only way, obviously. No, this is wrong, right? So where do we connect it? This? We can, well, I have something against multiple, but there must be some things. How many do we have? 1, 2, 3, 4. So I must have connected something wrong.